Thanks for sticking around. I'm going to be talking about reranking abductive proofs for plan recognition. So let's start with an example of, or what an abductive proof is. So given a set of existentially quantified observations O, so this is like in first order logic, let's say, an abductive proof of O is one that uses my background theory T, but also a set of assumptions A to prove O. Okay, so it's just like regular theorem proving, but I'm allowed to make assumptions. Okay, so let's do like a plan recognition example. So let's say I have these gray shaded atoms on the right. So I observe Bill going to the liquor store and Bill pointing a gun. And moreover, let's say I have these axioms relating action predicates to plan-related predicates. So I know that if there's a robbing going on and you're a robber and you're going to rob a particular place, you need to go to that place. If you're going to rob with a gun, you need to point the gun. Okay? So an abductive proof then of these observations might make some assumptions about what's going on that together with these axioms imply the observations. In particular, if I assume that there's a robbing going on, Bill is a robber, and that what he's robbing is a liquor store, all of a sudden I've proved my observations. I get this nice, tidy explanation of what's going on. Okay, so that's abductive proofs for plan recognition. There is one problem with this whole abductive scheme, and that is that there are always going to be exponentially many abductive proofs for any set of observations O. And that's just because I can always assume any subset of O. So given that I have all these proofs, I'm going to need to like pick the best one. And so previously the way people have dealt with this, so back in the day, people would define certain costs or other heuristics and they would search for the best proof. Recently, there have been these statistical relational formalisms like Markov logic networks and Bayesian logic programs. So these are attempts to integrate logic and probability. And what you can do if you do that is you can induce a distribution over your plan-related predicates, and so then you can find the most probable plan predicates or something, and that's how you can pick the right ones. We're going to try to actually just learn to score the logical abductive proofs themselves from data, and we're hopefully going to show that this overcomes some of the shortcomings of these more complicated statistical relational approaches. Okay, so first let's quickly talk about how MLNs work. So the idea is if I have some theory, right, so axioms, and I have a set of constants, what I'm going to do is I'm going to ground out all, I'm going to use my constants to ground out the predicates in my theory, get a set of logical atoms, and then I'm going to induce a distribution over these atoms, which are now going to view as binary random variables. They can be true or false. And the idea is I'm going to induce a distribution such that assignments to these random variables that satisfy more of the knowledge base are going to have more mass. They're going to be more probable. Okay? So let's just quickly see what that would look like. This is the same KB I showed you before. If I pick my constants to be the set C, and let's say I'm assuming that things are typed. So I can only use events to replace R variables, people to replace X variables, and so on. I'm going to get these 6 logical atoms by just grounding out the predicates that appear in this knowledge base. I'm going to make a Markov random field, an MRF, from these, and I'm going to view each of these atoms, each of these 6 atoms, as a binary random variable. Okay? So now I can have a distribution over these random variables, and like I said, what Markov logic networks do is they make it so that the probability, that when you have an assignment that satisfies more of the axioms, there's more mass associated with that assignment. Okay? And that's really the important thing to keep in mind about MLNs. Well, actually, let's go to the next slide first. So the way, whoops, that's the previous slide. Okay, the way this is guaranteed is we write the joint probability. So this bold X is like a binary vector of assignments to those atoms. And we're going to say that the probability is proportional to an exponentiated weighted sum of these Nj. And these Nj are the number of times the grounding of Fj, where Fj is just some formula in my knowledge base, is true. So assuming my weights are positive, right, then if Nj is bigger, then there's more mass for that, okay? So that's the idea. And so what you get is that the modes of this induced distribution correspond to the satisfying assignments with respect to the knowledge base. And that's why Markov logic networks are cool, okay? Great. So just to show you how you might think it would work, here is the same MRF from before. I have highlighted my observations, the going and the pointing in blue to show that they're clamped to 1. So we observe these, and now typically what we would do is MPE, most probable explanation, or map inference. We would try to figure out what is likely true given my observations, and this way we can maybe figure out what plan stuff is going on, okay? But there's a problem, and the problem is because, like I said, you only get credit for satisfying axioms, and because these conditionals, these implications, are always true if their consequents are true, once I've set go and point to 1, once I've set my consequence to 1, I actually get no probabilistic benefit from ever assuming the antecedents, right? The axiom's already satisfied. That's the only way I get mass in a Markov logic network, okay? So that's why you can't really do abduction in a Markov logic network framework, and so what we have to do to fix it is we need to basically add more axioms so that we get credit for assuming the antecedents, okay? And so people have introduced this idea of abductive MLNs, and like I said, you just kind of introduce more axioms. You're going to have, so let's say you have these P1 implies Q, and so on up to Pn implies Q, so you have a bunch of causes for a particular consequent. You introduce these hidden causes, these HI, one for each PI. You make these biconditionals between the PI and the HI, between the causes and the hidden causes. You say that each of the HI causes the Q, so each of these hidden causes are then sufficient for the consequent you care about. And this fourth bullet point is like the important thing. You also say that if Q, if your consequent is true, at least one of your hidden causes has got to be true, okay? And then if I ever satisfy this fourth axiom, then again I'm going to get credit for it, right? So this guarantees that I actually have more mass associated with assuming my antecedents if I've observed my consequent. Okay, and this last ingredient is also pretty important. I'm going to put negative weight unit clauses, which correspond to like low priors, on each of my HI. And so that way, even though I'm going to want to assume at least one of them to make this, this fourth axiom true, I'm not going to want to assume too many, and this way we sort of model explaining away. Okay? Cool. So let's see quickly an example. So these first two axioms in the KB are what we've seen before. I've added a third one, and this one relates also to going. So you might go somewhere if you're robbing it, but you also might go somewhere if you're shopping there. We can modify the KB using the scheme I just mentioned. I've done that here. And now let's look at the induced MLNs. This is now an abductive MLN, let's say. And what I'm going to try to argue to you is that doing inference in this abductive MLN is not going to capture a lot of the intuitions I think we have about how planned recognition should proceed. And so to show you that, let's work through sort of how inference is going to go, okay? So I've clamped point and go to 1, and now I'm going to want to figure out the most probable assignment, given that, right? Okay, so let's start with point. If point is true, then by that last axiom on the right-hand side, point H is true, the hidden cause for point is going to be true, so I'm going to assign 1 to that. By this third axiom, this third biconditional on the left-hand side, if point H is true, I'm going to want all those antecedents to also be true, so these are all the robbing things. So I'm going to want to make those true too, okay? So that's going to look like this. Everything, do you see that? This is lime, in case you like that color. So everything highlighted is on, okay? Now let's think about go, okay? So we said, so by this last axiom on the left-hand side, if go is true, at least one of its hidden causes is true. And like I said before, which one we pick is going to depend on which we have a higher prior for, okay? So let's say our prior for go H1 is higher. Okay, then we're going to pick go H1 to be true. By this first bicondition on the left-hand side, I'm going to want to make all that planned stuff on the left-hand side true. And so I'm going to assign those guys 1, 2. I'm going to get that. Okay, now go H2 is false. I'm going to want to satisfy the second biconditional on the left-hand side. And so because go H2 is false, I'm going to want to make all that stuff on the left-hand side, all that shopping-related stuff, also off, okay? So that's great. This is a great interpretation of what's going on. But what happens if my prior on go H1 is not higher than it is on go H2? In particular, if go H2 is higher, then I'm going to assign go H2 to be on. Again, by this second biconditional on the left-hand side, I'm going to want to make all the shopping-related stuff on to satisfy that biconditional. Go H1 is now off. Actually, let me just show you what that looks like. Okay. Go H1 is now off, and I can also satisfy this first biconditional on the left-hand side by just making sure that not all of the left-hand side is true, which I can do by keeping rob place off. Okay? And so the point I'm trying to make here is that you have this horrendous explanation of what's going on. You think the going is a result of the shopping, but the pointing is a result of the robbing, and yet this also satisfies all the axioms. Okay? And in Markov logic networks, right, that's how you get your probabilistic credit. Okay? So the point is this will satisfy all the same. Axioms will be just as probable with the exception of just these priors on the hidden causes. Okay? Thanks. Okay, so what I'm going to suggest is a way to kind of, I think, make use of, some robust intuitions we have about how we should do planned recognition here. So in particular, one thing you might think is that we should reuse assumptions. So if I already think there's a robbing going on and I'm using it to explain point, I should probably also use it to explain going. And also we probably have these pairwise regularities. If there's robbing going on, there probably isn't also shopping going on, at least if it's the same person, right? Okay, so that's what we're going to try to do. This is what I just said. And what we're going to try to do is we're going to try to use re-ranking. And in particular, what we're going to do is we're going to generate a bunch of candidate proofs so given a set of observations O, we're going to generate a bunch of candidate proofs, and we're just going to try to learn to select the best proof, okay? And, well, let's go to the next slide. Reranking is a popular machine learning technique in NLP. It's often used for structure prediction, where you need to predict a bunch of things all at the same time that have some internal structure. Typically in NLP, you would use a generative model to generate a bunch of candidates, and then you would train a discriminative thing to pick the best thing. In our case, we're just going to use a heuristic beam search to generate our candidate proofs for a set of observations, and then we're going to use our reranker to pick the best thing. Okay? And importantly, right, this discriminative model can incorporate arbitrary features, and so it can take into account what we mentioned before. So you need a loss function to train your reranker. This is a relatively standard loss function. I'm not going to go into the details. You can check out the paper. We modified it a little bit, but I don't think it's so important. The idea is if you have supervision, if you know what the right proofs are, then you can train your reranker to select the best thing. Okay, cool. What I do want to talk about, though, for a second is just the features we used. So there are these simplicity and coherence heuristics that Eng and Mooney mentioned a while ago, and these are supposed to be good properties of proof or plan DAGs, okay? We can just think of the DAG as the proof DAG, okay? So simplicity counts the number of explained atoms minus the number of assumed atoms. Coherence coherence count is the pairs of observed atoms that share a common parent in the DAG, and so if they share a common parent, right, one thing is explaining multiple stuff, and so we have that reuse idea. We also can use pairwise features. We can count when predicates or atoms are co-occurring, okay? And that way we can capture these pairwise regularities. And finally, these graph features, we can count the number of edges and nodes in the induced proof graph. If there's a lot of edges, if it's a dense graph, then things are probably more coherent. If it's stringy, though, then they're probably not. Okay, so we can look at, so again, you can check out the details of the search and all the stuff in the paper. I just want to show you, though, that doing this, you actually do really, really well. So we did this reranking under two settings. These first set of results are on this ACCEL corpus, which Eng used in 1992, and it was used by all these statistical relational people. Reranking ACCEL's own output, I think we do the best on this data set that's anyone's ever done, as far as I know. ACCEL itself does actually pretty well. And then just reranking a more naive search, we don't do quite as well, but we do better than all these complicated statistical relational approaches. We did the similar thing on another data set that people use, and we also performed quite well. And I think that's it for me. Thanks. Questions?
So I actually had two questions.
Great.
One was, it seemed like you were saying, I mean, the point of Markov logic networks, as I understand them, is that you get everything from coherence, right? And you don't have priors. But then all of a sudden, at some point you said, I mean, because this example, I think, is Charniak's. Mm-hmm. And yeah. I think it comes from, like you're going to the store and you assume initially shopping. I mean, it was created to sort of show why you need priors.
Okay.
Right? Because initially you're going to the store, you're shopping, you're not robbing.
Right.
Right? But then you point the gun and you know it's rob. And the second thing is that it seemed funny that you really, it seemed like by taking away these statistical relational features, or even a simple causal feature, it seemed almost like you were hiding information from yourself and getting it back, right? Because when there's robbing, you do all these things. Robbing is a package. But it seemed like it had been smashed out into an incoherent set of individual things, and then you were sort of getting it back later on, right? When you got robbing, why didn't you get everything else for free? It's because you had this funny implication structure that means that robbing doesn't imply all the good stuff you want.
Right. So I guess the point is, I think if you're suggesting that you could model a lot of this with an MRF, with a Markov logic network, that's certainly true. In particular, you can get pretty much any joint doing that, right? But the point is, inference would be incredibly intractable. The nice thing about doing re-ranking, and this is why it's used when you have these global feature situations, is you're always only going to have to pick from a list of length k. So whatever, you have 1,000 or 100 or something things. And you can have arbitrary features. So inference is always going to be lightning fast. Because as long as you can cut down your set to a reasonable set, and you can be pretty sure that a good answer is in there, then you can incorporate arbitrary features when you're selecting it. So I think you're right that Markov logic does have something to say about this, but the way people have applied it, and so what I've shown you is people have actually done this. And the reason they've done this is because it's pretty much just intractable to do anything more sophisticated than just weighting the axioms themselves. But if you made, let's say, higher order axioms, you could capture these higher order properties, certainly.
I don't see what's higher order about if there's a robbing, then you have to go to the store, and that's all I didn't understand is why
That's
is
not
it
higher
this
order, but
funny,
that doesn't
flat-
capture what else is going on, right? And if you wanted to capture what else is going on, if you wanted to capture these pairwise things, then that is higher order, right?
No, we better take this offline.
Okay,
Yeah.
sorry.
Yeah, I think we have to close the session because of the time. So thank you again.